Okay, it's my pleasure to announce the next speaker, which is E.G. Huang from Rutgers University, and he will talk about convergence in conformal field theory. Thank you very much.
Okay, thank you very much. So I'm very glad to be here. So unfortunately, I cannot be there in person, but because of the technology development, we can actually do this online. So that would be wonderful. Okay, so what I want to talk about for these lectures is mainly about these convergence problems in conformal field theory, and certainly which is in some sense equivalent to the representation theory of vertex operator algebras. So the convergence problem is actually of fundamental importance, but see, I think that especially in the beginning of the development of this whole theory, including conformal field theory and vertex operator algebra theory, people do not really pay too much attention to these convergence problems. So let me say that, for example, even just when BPZ have their paper study conformal field theory using the operator product expansion, okay, their method is just assuming, okay, you have two conformal fields, you multiply them, and then you can expand them as a series in Z1 minus Z2. So when you multiply two conformal fields, there's this first question, whether they are convergent. So these are always assumed, okay? And then see for some particular fields, people can actually calculate, okay? So, but this is not just for some particular model. It's even for particular models, it's only for particular fields you can do calculations. So then you see certainly you will get the operator per expansion. But to prove theorems in conformal field theory, we actually have to prove that this convergence holds for all conformal fields. So this is starting from the beginning, there's this problem of convergence. And then see later, Moreau has this really important work that they actually sort of proved the Verlinde formula and also derived some structure which is equivalent to these days we know that they are modular tensor category. But see, Moreau's paper are based on two fundamental conjectures. So one is the operator product expansion of what we now call intertwining operators. So they actually have a definition of an intertwining operator, but they call this chiral vertex operator, chiral vertex operators. So they assume that these chiral vertex operators satisfy operator product expansion. Okay. Then the second fundamental conjecture is that they assume that the Q traces of these products of chiral vertex operators are modular invariant. But see, before you can talk about modular invariance, the first thing that they implicitly assume that the operator product expansion, the Q trace of these products of chiral vertex operators are convergent. Okay, so these are the fundamental assumptions. And then you see in Moreau's paper, they also talked about high genus case. And in the high genus case, they also implicitly assume that you can obtain high genus conformal blocks or correlation functions from the low genus one. And this process also involves traces, which is, again, there is an assumption or conjecture on the convergence. So see, convergence problems are really, really fundamental. So basically, all these days, most of the results on the representation theory of vertex operator algebra, or the vertex operator algebra approach to the two-dimensional conformal field theory, they all depend on these convergence results. So for another thing important I would like to say is that the historically, first of all, convergence problems are always important. Historically, we have this Fourier series. Fourier series, if you do not really worry about the convergence, certainly you can use the Fourier series to do a lot of things. Then later, people prove that basically, say for example, all the continuous function. For all the continuous function, the Fourier series indeed converges to the original function. So in that sense, it's sort of like you can just study everything, almost everything using Fourier series. But for vertex algebras, it is slightly different. Is that in general, okay, these convergence might not be true. Okay, so we need some conditions. So this make the convergence problem become even more important because in general it's not true. You have to have some conditions satisfied. So this is another really important aspects of the convergence problem. So my talk for these talks, 3 talks, I will just present these basic convergence results. There are these convergence results we already have, and also some convergence conjectures. So the main thing that almost in every important steps, one has to prove some convergence. And for the rational conformal field theory, we basically proved these basic convergence now. Okay, rational conformal field theory, all the convergence problems have been solved. So you can just, based on these convergence problem, we can do the algebra. And also for the logarithmic theory, a large part of the convergence problems are proved. Okay, but the main sort of convergence are still conjectures are for general orbifold theory. Okay, so for orbifold conformal field theory, there are some special case like when the group is a cyclic group, then see one can use some results proved by Kanahan, Miyamoto, and then combine with my results, one can get these convergence. But the more general, like if you have, especially if you have a non-commutative group, these convergence are really a conjecture. So there is a conjecture, and then see for even more general case, these are even convergence problem because we still do not have a precise conjectures yet. Okay. And then the last thing I want to discuss is I myself actually developed the cohomology theory for vertex algebra. So this actually works nicely that all the usual properties for cohomology theory indeed are satisfied, and we even proved some theorem which connects the complete reducibility with the first cohomology and so on. But these results are all related to some convergence, and the main theorem for the complete reducibility needs some convergence. So there are some convergence problem for this cohomology theory. So these are I have to say that for cohomology theory, I even do not have conjectures. So these are open problems. So these are the main thing I want to discuss. Okay, so let me say that this series of talks, I actually have been preparing a paper which is invited for the Chinese Journal of Mathematics, which is in honor of a professor of mine when I was in China. So soon, I think I hope that at the end of March or beginning of April, I will post this review paper in the archive. So here I can just show you show you this paper. I almost finished. Okay, so so the material I discuss here, it will all be in here. Certainly, there's no technical details there, but see, I refer to the technical papers for the details. Okay. So I will give this online talk mainly using the iPad to write on this. So let me share the notes on my iPad so that I can write. I think that for such a talk, probably it's better to write. Okay, so here is the iPad. Okay, so I think everyone can see this, right? So what I plan to talk about. So this is the title, and what I plan to talk about. The first thing, okay, I want to quickly. This is first thing is something that which is very easy, and I think almost everyone studying vertex algebra knows this. But I do want to present this because I want to actually have a comparison. So this is about a rational function. And what I would like to call this algebraic convergence, because in this case, you are talking about a convergence, but see, it's not really a convergence. It's just an algebraic expansion. So in this case, basically, you can actually study everything using algebra, even though this is, if you use complex variable, this becomes some convergence. Okay. The main thing that if you only study, okay, the point is that if you only study vertex algebra or its modules, or even like a twisted modules, or some particular intertwining operator, then this method works, and which make things much easier. Okay, so in some sense that in the beginning people do not really worry about convergence is mainly because of this, because for vertex algebra you sort of do not have to prove this kind of a more difficult convergence. Okay, so I will discuss this, but whenever you actually go into the general intertwining operator, then you will have to seriously use you have to use the complex variables and differential equations to prove convergence. So here the convergence for general intertwining operator, it is not just some kind of like a suitable function you can expand them into series, because we also have to use analytic extensions. Our proof of the convergence, it's not just you prove that this series is a expansion of some function. We actually have to use the analytic extension. So this actually is actually something that which is probably very deep, is because whenever you get into intertwining operators, sort of you have to get into the fields over complex numbers. So vertex algebra should be over the complex number. If it is over some other fields, you will not be able to get such nice results. Okay, so I think this is really deep, because this is related to, say, for example, probably like the difference between geometry long length program and the long length program. So a lot of nice things actually works for geometry long length program, but it might not be so easy for the long length program. Certainly, so in the future, it will be actually interesting to see whether these things can be generalized to other fields. Okay, but at this moment, these are really over the complex fields. So this is whenever we actually study this kind of a convergence of like products of intertwining operators. So the reason why for intertwining operators the problem become more difficult is because intertwining operators are multi-valued. So the main thing that when we study representation theory of vertex algebra and also conformal field theory, we are actually studying the chiral conformal field theory. Okay, so if you have a full conformal field theory, sort of the conformal fields must be single valued. But see, when you study chiral conformal field theory, these conformal fields, chiral conformal fields, are multi-valued. And actually, the deep thing actually coming from these multi-valuedness, like the break group representations and so on. So they are all coming from this. But this also makes the study of these intertwining operators become much harder because, if it's single valued, sort of, I think that one can prove that because of an intertwining operator property, together with single valuedness, I think one can prove that their correlation function or products, they must converge into a rational function. Therefore, we can use the first part to actually discuss this. Okay, so this is the second topic I want to talk about. Then the third topic is about the convergence of the, in general, it will be so-called pseudo trace. But in the rational case, it is just a pure trace. So these are also products of intertwining operators. So this is important because these are actually certainly the goal is to prove these pseudo Q traces satisfy the modular invariance property. It means that these pseudo Q traces, they should form they form a vector space. These vector space actually under the action of the modular group is invariant. Okay, so this is the goal. But see, if you want to prove this modular invariance, you first have to prove that these Q traces must be convergent. Otherwise, you do not get. See, you have to prove they are convergent so that you can actually even talk about the modular group action. Okay, and then see these pseudo Q traces are actually give us after the modular invariance is proved, then these give us all the genus 1 correlation functions. Okay, so this will actually lead to the conclusion that all the genus 1 correlation functions can be obtained from genus 0 correlation functions. Because intertwining operators are nothing. See, intertwining operators are nothing but the 3-point functions in chiral conformal field theory. Okay, so this is the number 3. Then the fourth part. I want to discuss. There are there is a definition of conformal field theory by Graham Siegel. Okay, so Siegel defined the conformal field theory by just use a two-dimensional conformal field theory in the sense of Siegel is just some kind of a representation of a geometry category. The geometry category is formed by the objects are just the circles, and the morphisms are Riemann surfaces connecting these circles. So the composition of morphisms are just the sewing of the Riemann surfaces. So Siegel has this definition, and then you see if we want to prove that if we can use vertex algebra representation theory to construct the conformal field theory satisfies C equals axiom, we actually have to have these maps associated to Riemann surfaces. So between these different modules. So these are, in general, it will involve the arbitrary boundary parametrization of the Riemann surfaces with boundary. Okay, so when you have arbitrary Riemann, the boundary parametrizations, okay, when you do the sewing, you will have some convergence. So because we start with, say for example, we start with some vertex algebra modules and the intertwining operators. So they are just a representation of the Chiral algebra, which is a Lie algebra, which is the infinitesimal conformal symmetry. You can view them as infinitesimal, the local, the boundary parametrizations. So you have to sort of expatiate them to make sure that indeed this sewing operation corresponds to things that which are actually convergent. Because whenever you want to exponential some Lie algebra, the convergence is always a difficult problem. So so here is something that I want to briefly explain: the convergence involving the Chiral algebra and determined line boundary. The reason why determined line boundary must be involved is because we have the conformal anomaly. That's the central charge. The central charge can only be dealt with using the determined lines. Okay, so this is the fourth part I will discuss, and then the fifth point I want to discuss. This is relatively recent. In mathematics, it's still counted as a recent result, but in physics, probably it counts as a result like 2 years ago. So this is a high genus convergence result. So this is by Bing Gui. Okay, so this is a 2-year result. He proved this. This is result. See, it is necessary if you want to construct the high genus rational conformal field theory. His result is only for rational conformal field theory. I actually proposed this convergence as a conjecture, and then he proved this. So this is very nice. And the last part I want to discuss are just this is not the last one. The next to the last one, it's a conjectures and a problem the convergence in orbifold theory. So in some sense that at this moment, the orbifold theory has not been fully developed is because these convergence conjectures and problems haven't been proved. Okay. Then the last topic I want to discuss is the convergence problems in the cohomology theory. Of VOA. Okay, so this is the outline of my lectures. So I will start with first of all, this is simple thing. Okay, so I do want to discuss this because I want to compare with later the convergence problem for the intertwining operator. Okay, so this is the first topic. Okay, so here the main thing is the following. For rational function, the convergence problem become really easy. So here what we usually do is the following, is that assume that, so here you see we even do not need anything like the concept of vertex algebra. We only need to say we have some kind of meromorphic conformal fields, say AZ. This is a map from a vector space. This vector space must be graded. So usually this is the vertex algebra or the module for vertex algebra. So assume that we have such a map, and here the V, we assume that it is of this graded by Z, and also Vn should be equal to 0 when n is sufficiently negative. Okay, and then we have assumed that we have another such meromorphic fields. So the main thing that the corresponding fields is just a Laurent series. It's not non-integral power and so on. And we assume, so that the usual assumption is that we assume this so-called weak commutativity, or sometimes people call this the locality. Okay. So if this is true, then we can show that basically the product AZ1 BZ2 is convergent in a suitable region. So the reason is this: the proof is simple, because in this case we can just take this V prime, which is the graded dual of V, and there's Z1, B, Z2, V applied to another V. This is certainly equal to Z1 minus Z2 to the nth power, and V prime BZ2 AC1. Okay. Now the main thing is the following. We actually also assume that AZ can be written as sigma AN C to the minus n minus 1. You can expand this as into its components, and we assume that the grading of V is called weight, and then CD will assume that this operator AN has the weight. AN is equal to some number, we call this weight A, and then minus n minus 1. Okay, so we assume this. If we assume that the weight has this type of property, then one can actually easily see, okay, so B also satisfies this kind of a property. So we can easily see that this part contains only finitely many negative power of Z2. And we can also see that this AZ1 pair with V prime contain only finitely many positive power of Z1. So and then you multiply some polynomials. So this whole thing has only finitely many negative power in Z2 and finitely many positive power in Z1. But the other side, you only have a finitely many negative power in Z1 and a finitely many positive power in Z2. These two equal means that this must be equal to a Laurent polynomial, right? This must be equal to a Laurent polynomial in Z1, Z2. So therefore, you see, if you want to see, our goal is to show that this is actually convergent. This point is convergent. So we already know that this is equal to a Laurent polynomial. So we only need to divide both sides by this z1 minus z2. The only thing that when you divide, you have two choices because this is a positive power, so this must be a polynomial. But when you divide, there are two different inverse. So one inverse is that you can expand in the positive power of z2. The other is in the positive power of z1. So because this series has only finitely many negative power in z2, so when we divide, we must expand this as a series in the non-negative power of z2. Okay, so then CD we obtain that v prime a z1 b z2 v must be equal to something like this gz1. This is a polynomial in z1 z2, and then the z1 r z2 s z1 minus z2 p, where z1 minus z2 must be expanded in the non-negative power of z2. Okay, so if we have this kind of expansion here, it means that in this region z1 bigger than z2 bigger than 0, this series must be absolutely convergent to this rational function. Okay, so we prove the convergence in the region, and also the sum of this series can be analytically extended to the whole space except some singularity. Okay, so this is this is actually the part one, which is very easy. Okay, so you see that if we have such so-called local fields, meromorphic fields, then see the convergence is really easy to prove. Okay, so now really comes to the difficult part. That's about intertwining operator. Yeah, so let me mention that this approach, certainly here I just described this approach to be work with these fields which are actually Laurent series, okay, and then satisfy this locality. This can be generalized to the case that this AZ1 BZ2 does not have to be Laurent series. They can have the some kind of a non-integral power, even logarithm. But to apply this approach, you must have this locality. It means that z1 minus z2 raised to sufficient integer power applied to this should equal to, you just switch the order of the product. So if this type of property holds, then you can still use this approach. But unfortunately, for intertwining operator, this is not true. Okay, so the second part now, this is the first main thing I want to discuss. We actually wanted to discuss more general intertwining operators, whether the products are convergent. So let me quickly recall what is the intertwining operator. So first of all, we do have to have a vertex operator algebra. So vertex operator algebra now, it is the direct sum given by this and satisfy some condition. Here I just mainly want to mention this property because this is related to what I want to write for intertwining operator. So it's like so this is a vector space. Then we have to have a vertex operator map, which is from V tensor V to V. And also we, so this is the notation we usually use is YU XV. And we also have to have a vacuum. Okay. Now for the product of intertwining operator, we actually do not really need the full Virasoro algebra. We do need SL2, but we do not need the full Virasoro algebra. Therefore, you see, we do not need this conformal element. SL2 actually, we do need L minus 1, L0, and L plus 1. So L minus 1 can be defined using the derivative of vertex operator. And L0 is given by the grading, and L plus 1 is the adjoint of the L minus 1. So in some sense that these are coming from this structure. So the main property I do want to actually emphasize is that if you look at the vertex operator book, mostly the axioms are given by like a Jacobi identity or locality. But here I do want to emphasize this axiom that because we describe the intertwining operator using this. So you just write down the action of the two vertex operator on a vector and then pairing with its graded dual. And you can also certainly write down the opposite order one. And you can also write the other, that is the YV of, so this is, we call this the iterate of two vertex operator. Okay, so the main axiom is that all of these are absolutely convergent. So they are absolutely convergent. In the region that the first one is in this region, this is something that we have seen. The second one certainly should be in this region because the first one already said that the second one should be convergent in this region, and the third one should be convergent in this region. Okay, and they should converge into a comma. See, the main thing that they should converge to the same rational function. Of this form. The form is just what I actually wrote down. That is the GZ1 C2 over Z1R C2. Certainly here, when I write down these RS are all integers. RST. Okay, so this is the main axiom. So there are some other axioms I will omit, but this is the main axiom for a vertex operator algebra. And then see we certainly have a module. Module is the main difference is that now module, first of all, the grading must be in general. It will be the graded by complex number instead of the integers. And if this is a rational conformal theory, then one can prove that it will be graded by rational number. But in general, we have to assume that this is graded by complex number. And there is a vertex operator, which is just like an action of the V on W. And it should satisfy all the axioms for vertex operator, which still makes sense. So in particular, this so-called duality property or commutativity, associativity still holds for module. The only thing that for module, what you need to do is that you replace this by vertex operator for module, and here you have to replace this by W and W prime. These are in W and W prime. And this become also vertex operator for module, and this is W prime. And here, this should be the vertex operator for module, but this, what's inside, is still the vertex operator for algebra. Okay, so then these still should be convergent in the corresponding region to a rational function. So module, the things looks almost completely the same as algebra. There not much difference. And so I want to mention that because of the part 1 here I discussed here, this kind of property, then see this main axiom for vertex operator algebra can be proved easily using the method here. Okay, so the main thing that for familiar example of vertex operator algebra, it's easy to verify that some of these fields satisfy this kind of a locality or weak commutativity, and then you can use this to prove these. Okay, so this is the module and algebra. So now I will discuss the intertwining operator. So this is the main thing. So here, see, I do want to mention that sometimes there's this confusion. People think that vertex operator algebra are corresponding exactly to the conformal field theory, but actually it's not, because there's this terminology sort of confusion, because Moreau called intertwining operator chiral vertex operator. So people might think that the vertex operator gives everything, but in mathematics, vertex operator algebra has only these so-called meromorphic fields. The intertwining operator are the general conformal fields, which is not meromorphic, which is multi-valued. So the main, okay, I should say that the main object for us to study in conformal field theory are really intertwining operators. So intertwining operators are actually defined, so we need modules, like 3 modules. If we have 3 modules for vertex operator algebra, then see an intertwining operator should be a map from this tensor product to some series with coefficients in W3, but the general case that the most general, so let me just write down this. So it is a series. This notation means the series with non-integral power. So it can be complex power of X. So this is a series with complex power of X, and you also have to have logarithm in general. Okay. So what's the reason? See, certainly you can always study this, but see what is the reason that first of all you need this kind of general sort of a series and even logarithm. This can actually be derived. So actually there are some relations must be satisfied by say for example a 3-point function. And a 3-point function in the beginning is that for each say for example sphere with punctures, you actually can define such property, and then at one point you can define some map satisfy this property, and then this intertwining operator will have to satisfy certain so-called we call this L-1 derivative property. This L-1 derivative property corresponding to a differential equation. And then you see, you solve this differential equation, you will see that you sort of start with at one particular value. This particular value is just something satisfies certain property. So you already have this value, and then you see you solve the differential equation, you will see that the general solution must be of this form. Okay, so this is something that it's conceptual. It's not just we imposed on this. Certainly, see this certainly also coming from the physical example and the mathematical examples. But see, this is the also can be derived. Okay, and the intertwining operator should satisfy mainly 2 properties. The first property is the following. See, now we can take the W3 prime. So because y coming out to y is W3. And then sorry, let me first put y W3 is the module map acting on the algebra, acting on the module W3. And this is the intertwining operator. You can put y1 here. and a Z2 here, W2. Yeah, so W2 here. Okay. So here I do wanted to actually emphasize, because this is crucial, because this is see, when I write such a series, there's no problem because it's a formal series. But when you want to substitute complex variable, you have to be careful, because this is you have a Z2 to the non-integral power, and also you have a logarithm Z. When you substitute, you have to choose a value. Okay. So usually we choose the value in this way. We always choose like a logarithm Z. We just use the convention that logarithm Z means that absolute value of Z plus the argument. See? So here we require that the arguments Z is bigger than or equal to 0, less than 2 pi. Okay, so this is our convention. Okay. So when we write on this with Z2 substitute for X, we always mean that you use this logarithm of Z2. Okay, then this choose branch for either power of the of Z or the logarithm of Z. So this is one part, and then the other part is you switch the order Y, W1, Z2. Here you have to apply this to the W2. And then the we have this iterate. Okay, here it's you have to apply to W1. So here it should be Z1 minus Z2. Okay, these three series, they should all be absolute convergent in this region, the corresponding region I already wrote down before. And this Z2 Z1. So they should be convergent, and they should be convergent to the same. In this case, it's not a rational function, but it is still a it's just a multi-valued analytic function. They should converge into a same multi-valued analytic function, but there are three singularities. No, it's not three. It's just these are the singularities. Z1, Z2 equal to 0. This is singularity. Yeah, actually it's a 3. Minus Z2 equal to 0. This is another singularity. So the main thing that these two singularities are not poles anymore, because the intertwining operator has contained non-integral power and logarithm. So these are not pole, these are branch points. But this, at this point, at this point it must be a pole. Why? Because here, you see the dependence of Z1 minus Z2 you can see from here. Here, this is just the full module, and this is only have a pole. So we know that this function must be a multi-valued function, but with branch point at Z1, Z2 equal to 0, and pole at Z1 minus Z2 equal to 0. Okay, and this can be and it extends to the whole region except for these singularities. Okay, so this is then certainly there's another important property, that's the derivative. This should be equal to just the y of L minus 1. So I said that we do need L minus 1, even though we do not need the whole Virasoro. Okay, so there should be some kind of a vertex operator L minus 1 acting on the W, and the derivative of this is equal to this operator. Okay, so this is the definition of intertwining operator. Okay, if you have vertex operator, you have modules, then you can talk about intertwining operator. So intertwining operators are nothing but the 3-point correlation functions. For the chiral conformal field theory, if there is a chiral conformal field theory. Okay, so now we actually the main thing we are interested is there are two things, but these two things are the same. First of all, we must consider if we have two intertwining operator, and there's another intertwining operator. Okay, so assume that because the in general intertwining operator will come out some module, say W3 or something. So you have to make sure that the incoming module for Y1 and the outgoing module for Y2 are the same, so you can compose them. You can take the product. Okay, so when we take these products, okay, so actually the both Belavan, Polyakov, Zamolodchikov, and Moreau, they actually formulated this. The fundamental conjecture in conformal field theory is that we should have the operator approximation. So these are the basic conformal fields, chiral conformal fields. You should be able to expand them as a series in powers of Z1 minus Z2. Okay, and with coefficients to be some fields, conformal fields in Z2. Okay, so this is BPZ and Moreau. They formulated this operator approximation, and then later I think Gurari, he actually first the explicitly formulated that the operator approximation in general, you have to not just expand as Z1 minus Z2 to some power, but also have to have logarithm. Okay, so this is something that in some cases you cannot avoid logarithm. Therefore, this is the logarithm conformal field theory. So here, but see, I just want to mention that before you can even talk about this expansion as some kind of expansion in the Z1 minus Z2, no matter whether it's a power of Z1 minus Z2 or logarithm of Z1 minus Z2, you first have to make sure that this is a convergence. All right, without a convergence, because these intertwining operators in the beginning, they are just some series. Okay, when you multiply two series, infinite series in general, certainly with two different variables. Sorry, here it should be C1. With two different variables, you can write on such a series. But whether it's convergent, this is a main question that we first have to answer. Okay, so this is the first part that we actually have to prove this convergence. Okay, so the main sort of interesting but also make the theory more complicated is that this convergence is certainly not true. It's not true for all vertex operator. So this is not true. Only for some vertex operator satisfy some conditions. Okay, so that's make the theory more subtle. Okay, so it's not certainly for the familiar theory. Indeed, we can verify that these conditions for this to be true holds. But see, this is the reason why this convergence is really important. It's not like for every vertex operator, you take any two intertwining operator, it must be convergent. So here, it is actually important for us to introduce some conditions. So this is without these conditions, these will not be convergent. So we have examples. So here the convergence, the condition I introduced more general one because later when we discuss the Q traces, we need C2 cofinite. So here we need only the C1 cofinite. But there's the Cn cofiniteness condition. And the Cn, the under suitable conditions, Cn follow from C2. So usually we only discuss C1 and C2. So this convergence is the following. So this is a module. Okay, so there are some results that the C2 cofiniteness algebra implies C2 cofiniteness are module. So I will discuss later. This convergence is the following. Assuming that we have a module, okay, and then we give this space this C1W, CNW, sorry. I want to discuss the general case. CNW is equal to, okay, this is the linear span, so I use this notation to denote the linear span. Linear span of elements of this form, residue x to the minus n, and then yw, this is the module map, v x w. So here, v is in the so-called v plus. V plus is the direct sum of all homogeneous subspace with n inside C plus. So it's a weight are positive, and W is certainly just in W. Okay, so it's a linear span of this. And then the what is C1? What do we mean by W is Cn cofinite? It means that the dimension of W over Cn W is less than infinity. Okay, so this is the definition of Cn cofiniteness of a module. And for this, for the discussion, the proof of the convergence of the products, we only need C1 cofiniteness. Okay, so this is it's actually quite nice. Like the basically C1 cofiniteness is for like a product of intertwining operator to be convergent, and these products of intertwining operator corresponding to genus zero theory, and it actually corresponding to the if we study the tensor category theory corresponding to the braided tensor category. So C1 cofiniteness is actually the main sort of condition for these genus zero theory and braided tensor category. But then see, if you want to go to genus 1 theory and a high genus theory, then we have to use the C2 cofiniteness. And then see the also if the tensor category you want to the tensor category to be modular tensor category, which will actually have much better properties, so that you can get the three-dimensional three manifold the invariance. So we have to have the C2 cofiniteness. Okay, so now the assume. Okay, so now what we want to do is the following. So here is the we actually have two intertwining operators. So we also wanted to take the always want to study these things by apply to some elements and pairing with some element in the graded dual. Okay, so we wanted to, when we talk about the convergence, what do we mean by the series is convergent? So we certainly apply to element and then pairing with some graded dual element. So this become a series with terms to be complex numbers instead of operators. So we want to prove this is a convergence. So here we have to assume that all these W1, W2, W3, W4 prime. These are four modules. So here it's W4 prime, not W4. Okay. These four modules, they must be C1 cofinite. Okay, so this is the assumption we actually need. Okay, without this C1 cofiniteness, we will not be able to prove the convergence. Okay, I think that yeah, actually in my paper proving the convergence, there's a remark saying that I think one of the module does not have to be C1 cofinite. So indeed, we can slightly weaken the condition, but see, the spirit is always that the module should be C1 cofinite to make sure that we have this convergence. Okay, so the proof of the convergence.
Naive question.
Yes,
so,
please.
Are the intertwining operators always assumed to be quantum fields?
Yeah.
Okay.
These are intertwining operators. So here you see we actually, when we start with the vertex operator modules and then intertwining operators, these intertwining operators, they are just corresponding to the chiral conformal fields the physicists talk about. They are exactly the same. So if you look at Moreau-Seiberg's, they actually describe the axiom for the chiral vertex operator. It's exactly the same as what we call intertwining operators. Okay.
Okay. Thanks.
Okay. Yeah. So that's actually the important thing. Okay. So because for example, if I can prove this is convergent to the NCT, I proved both the basic assumptions in BPZ and also in the Moreau-Seiberg. Okay. So now the method to prove this convergence is the following. See if you are given two explicit quantum fields, if these are like a very explicit one, like for example the stress energy tensor, or some like the invest-to-minute model, the basic fields associated to the alpha Lie algebra. Then see it is possible. Okay, in general it is extremely difficult, but see for some explicit fields, it is possible to use explicit expression to prove this kind of a convergence. But see we actually wanted, first of all, see this kind of a mathematical theorem. I think that it's we actually in mathematics we want to prove theorems such is something like this. We want to prove the theorem to be the most general, but also we wanted to show that under some condition the theorem should be true, and if this condition is not satisfied, the theorem is not true. So we wanted this kind of a sharper result. Okay, so if you calculate the explicitly some field, it does not help us to actually prove this. So if it's not explicit field, then it is actually, you cannot use any explicit calculation or something like that. You do some kind of estimates. That's impossible because it's so general. Okay, these things are so general. It's just some general map satisfies certain property. So the only method is actually to use the differential equation. There's no other method for such a general convergence. So what we do is the following. We actually show that this series satisfy a differential equation of regular singular points. Okay, so certainly when I say the series satisfies such a differential equation, I mean that the differential equation itself, the coefficients can all be expanded using series in suitable region, and then this series satisfy the expansion of that differential equation. Okay, and then you can use the general theory of the differential equation of regular singular points. That is, if you have such a series solution, the series solution, the at most involve finitely many non-integral powers and also some logarithm. If the series is of that form, and then satisfy the differential equation of regular singular points, then this series must be convergent to a solution of that equation, and the solution of the differential equation of regular singular points must be an analytic function, but in general it's multi-valued. Okay, so this is the way to prove this, and this sort of general theory of differential equation, roughly speaking, is like any solution of regular singular points near a singular point can always be expanded as a series of the same form. And then see the main thing that if you, because for such a differential equation, a solution is determined by the first few coefficients. So if the first few coefficients are determined, then you see the whole solutions are determined. Therefore, if you have a solution, if you have a differential equation, you take the first few coefficients of this series, and it should give you a solution. Okay, that solution is analytic, but we know that the solution can always be expanded as a series, and then see these series must be equal. The reason is because the first few coefficients determines everything. So because these expansion are equal to this series, so we see that this series is expansion of a solution of the differential equation, and therefore it just means that this series is convergent to some analytic function. So this is the idea. Okay, but how do we derive the differential equation? So here we have to use the C1 cofiniteness. So this is a crucial thing. Without this, we cannot derive the identity. So here the main thing is that we need to derive some identities. Okay. So let me say the following. So we use the C1 cofiniteness to derive some. Now, actually, we first derive some identity, and then we can use the C1 cofiniteness to actually obtain the differential equation. So here, let me explain the idea. Certainly, I will not be able to give all the technical details, but see, I think the idea is very clear. So the first thing we actually can prove is the following. Okay, let me use a notation. So here, when I define the C1 cofiniteness, okay, so here it's a Cn cofiniteness. Cn cofiniteness is spanned by elements of this form. So we actually, for simplicity, let me just use the Borchert's notation. Borchert's notation is that this residue of this vertex operator is written as U minus N W. Okay. Let me use this notation. See, these days sometimes I try to avoid this notation because this will confuse with like a U sub 1, U sub 2 if you have two elements or something. But here it is indeed convenient for me to use this. So here now, it just means that for C1 cofiniteness, we actually need to consider this U minus 1, right? This U minus 1 applies to some W module element. So we actually now want to prove the convergence of this. So we first derive some relation for series like this. So the first relation I can write down is the following: W4 prime Y1. Here it's U minus 1 W1. So the difference is that I apply U minus 1 to this, and as U1. Okay, then I obtain this identity. So the proof of this, you just need to use so-called the Jacobi identity between actually only part of the Jacobi identity for the vertex operator on modules and intertwining operators. So we only need to use so-called associated formula and the commutative formula. So anyway, this is something that it's a technical calculation. It's not difficult. It's just it's something you just do some standard calculation. Okay, so let me see. There are some coefficients here. Okay, here it's a Z1K. And here, okay, so here, let me first write on this, then I explain the notation. Okay, it's a U minus 1 minus K star, W4 prime, and Y1. here, this u1 minus 1 u minus k star is the following. You see, originally this is supposed to be u minus 1 minus k applied to this y1. Now you can just take the adjoint. So star just means adjoint of u sub minus 1 minus k. So I already explained u minus n, so it should be clear. And then you see the plus the following term, sigma k also in n. These are non-negative integers. And here will be z1 minus z2 minus 1 minus k w4 prime y1 w1 c1 y2. So here it's uk w2 c2 w3. Okay, so here uk is also I explained this is one component of the vertex operator acting on w2, and then there's one more term k n z1 minus 1 minus k uk applied to w3. Okay, so this is only one of the identity. Okay, so here the one of the identity is the following. It just reduce, if you have an operator acting on w1, you can just write this operator acting on w1 as some operator acting on w4 prime, acting on w2, and acting on w3. So that's the meaning. And there are actually three others. Okay, so for example, here you can put u minus 1 acting on w2, and you can also express this as acting on others. And then you also have u minus 1 acting on w3, or u minus 1 acting on this w4 prime. So we have four formulas. Okay, so why these formulas will allow us to derive differential equation is the following. Just remember, our modules are all C1 cofinite. Okay, C1 cofinite means that almost every element in the module can be written as this form, right? Almost every element, except for a finite dimensional space element, you cannot write this as a linear combination of such element. So we just have only finitely many elements, because if it is a finite dimensional space, you can take a basis. The basis has only finitely many elements. So basically, we only have a finitely many elements which cannot be written in this form. Okay. So and then see for all the other infinite dimensional elements, you can always written in this form. If you can written an element in this form, you can always write in these three terms. And these three terms, you look at mainly look at the weight. This weight must be less than the weight of w4 prime. So this is something that's easy to see, to calculate. And this weight is also less than, it's a strictly less. This is also strictly less. The weight of this is less than w4 prime. The weight of this is less than w2, and the weight of this is less than w3. So you can use this induction except for like a finite dimensional space of elements. All the other elements in w1, when you have the action, you can always reduce them into linear combination of elements involve all these elements like a w4 prime, w3, w2, w1, for which the weight is less than, because you can successfully use this procedure. So you can always reduce these weights to be sufficiently less than some number. Okay, to be the weights can always be reduced to something that the weight are less than some number. So the except of finite dimensional space. Okay, so these finite dimensional space, you can they always contain in some subspace of the module whose weight is less than something, right? Because if the finite dimensional space you have a weight arbitrarily large, it will not be finite dimensional. So see, basically the any kind of any element. So for any W1, W2, W3, W4, okay, you can always write this series as a linear combination of a series with W1, W2, W3, W4 prime to have a weights less than some fixed number, okay? And because our module, we also assume that they have to be so-called low bounded or quasi-finite dimensional. So the main thing that for every module, the dimension of the homogeneous subspace whose weight are less than a fixed number must be finite dimensional. This is one of the condition we need to use. So because of this, so for arbitrary the W1, W2, W3, W4 prime, it is always equal to the linear combination of only finitely many such series. Okay, so what does this mean? This means that if we look at the module, okay, so here I want to say that if you look at the coefficients, these coefficients are actually inside of this ring. Ring is the C1 plus 1, C2 plus 1 minus 1, and C1 minus C2 minus 1. So it is the coefficients are all in this ring. Okay, so when you write out linear combination, you have these coefficients, and therefore I just want to say that this as the space of this series as a module over this ring. Certainly, you generate a module over this ring must be finitely generated, right? So it must be finitely generated. So anyway, the main thing that because of this, so you can take the derivative. We can take the derivative. So we only need to consider finitely many such series, right? With only W1, W2, W3, W4 in some finite dimensional space. So we only now discuss, say, for example, only these particular series. We now take the derivative. So we now take the derivative, but the L minus 1 derivative property says that this is equal to this. Okay, but no matter what this element is, we know that such a series can always be written as a linear combination of the finitely many elements we start with, right? So the derivative now, the derivative of one of the finitely many elements, finitely many series, can always be written as a linear combination of the finitely many element series we start with. So this is a differential equation. Okay, so this derivative is for the Z1. We can also do this for Z2. So we have a system of differential equations. Certainly, so this is the derivation of a differential equation. Another way of deriving this is originally I did in my paper is because this the space of the series generates a finitely generated module. Therefore, you take higher derivatives for fixed element. For such a fixed element, W1, W2, W3, you take higher derivatives, so you generate a module. These higher derivatives generate a module, generate a submodule, and this submodule must also be finitely generated because our ring is Noetherian ring. So this ring is Noetherian. So you have a finitely generated module for all the derivatives. So these derivatives must have a linear relation, and therefore we obtain a higher order differential equation. So basically these two things are equivalent. Okay, now, but see, I should say that the idea of this deriving differential equation is actually very sort of relatively simple, but we actually have to prove that this has regular singular points. Only have differential equation, you still cannot prove that these series are convergent. Okay, then see, you have to be just use more careful analysis, because see here, this is z1 to the kth power. Here it's u minus 1 minus k. And this is a z1 minus z2 minus 1 minus k. Here it's uk. Here it's uk. Here it's z1 minus 1 minus k. You see these number k here, the minus 1 minus k here, they are actually has some kind of property. Using these subtle, more subtle property, we can indeed show that the differential equation is regular singular points, and therefore this is convergent. Okay, so it is the series using the differential equation. We prove that if this proof if you just look at the convergence part, we see that we do not need arbitrary module to be C1 cofinite, only these four modules to be C1 cofinite. And I think in my paper, actually, I said that one of them do not need to be. So this is some results that we can actually have relatively weak condition to guarantee the convergence. But certainly, the next step is that if you want to prove this is equal to the iterates of some intertwining operator, then you need more conditions. Okay, but for convergence, we only need this. Then the next thing I do want to discuss the analytic extension. So here I just want to say that this differential equation, if you look at the coefficients, see in this equality, the coefficients are z1 to some power and z1 minus z2 to some power and z1 to some power. Here it is important that when we write down this z1 minus z2 to some power, if you view this as a series, you must expand this z1 minus z2 in the non-negative power of z2. Otherwise, it will not be equal to this side, because this side has only our assumption on module will actually say that there are only finitely many the negative power. Because it's complex power in general. See you will say that finitely many power with the real part is negative. So because of this, so here you must expand in the non-negative power of z2. Otherwise, you will not get a formal series, well-defined series. So because of this, actually the differential equation we derive, okay, the differential equation is actually is actually for this formal series. So when we derive differential equation, the coefficient of the differential equation certainly are in this ring, but actually when we write down the differential equation, it's not an element in this ring. It's the expansion of elements in this ring in the non-negative power of z2, right? So this must be expanded in the non-negative power of z2. So what this means? This means that the coefficients of the differential equation, which is now a series, is actually convergent in this region. Because the coefficients are actually the expansion of series z1 minus z2 in non-negative power of z2. So the coefficients must be convergent in this region. Okay, then you see basically the differential equation theory says that if you have coefficients actually convergent in this region, then the solution, okay, the formal solution, the series solution must also be convergent in this region. So we actually have the convergence in this region. Okay, so this we proved that it satisfies differential equation, and then we also proved that using the differential equation theory, we proved that this is convergent in this region. So this is where the region coming from. Okay, and then you see because the coefficients are elements in this ring. Okay, elements is in this ring has only singularities at z1 equal to 0, z2 equal to 0, and also z1 minus z2 equal to 0. These are the only singularities. Okay, therefore just using the theory of differential equations, the solution also has only singularities at these points, but the difference is that the coefficients has poles at these points, but the solution in general will have branch points at these points. So from this, we can immediately know that this series is not only convergent in this region, but it can be analytically extended to to actually C2 minus these singularity point. Okay, but the main thing that the analytic extension in general will be a very complicated multi-value function, because all these 3 points can be branch points. Okay, so you will not be able to find an expression similar to the rational function. So sometimes people, if you wanted to generalize the method we use in the discussion in the beginning, then see this approach does not work here, because that approach actually the main importance is that you can multiply some z1 minus z2 to some power, and then cancel the bad part, and then see you will get very nice things. So you can divide the bad part again to obtain the function it converges to. But in this case, there's no such thing you can cancel. Okay, so you cannot multiply anything you can cancel, because these are multi-valued function with all these branch points in general. Okay, so only in some special case like z1 minus z2 is a pole, and then you can use that method. Okay, so I think today I should just finish it here, because I think it's already time. So tomorrow I will continue. I will continue to discuss the pseudo trace of this product of intertwining operator.
Okay, so let's thank the speaker.
Okay, thank you.
Do we have any questions in the audience? Or in Zoom, then just speak.
So what's the question?
So you said that the equation you obtain has regular singularities.
Yeah.
I have not understood why it is important in your argument and why it is true.
Yeah. First of all, we have to have the singularity must be absolute convergent. Regular singular, because for regular singular point differential equation, the solution near the singularity points can be expanded as a series in the form that our intertwining operator did. Okay, so because of this, so you can actually say that the expansion of a solution is the same form, and the coefficients are the same, and therefore these two series must be equal. So our series we start with is equal to the expansion of a solution of the regular singular point differential equation, and therefore it must be convergent. If not the regular single point, we do not really know whether the solution we actually want can actually be expanded as a series in this form. So that's the need why we actually needed to prove this.
This is why somehow you limited the functions you can use at the beginning to this.
No, actually, yeah. So in some sense, that you can say that why limited the function this way. But see, as I explained, when we actually define intertwining operator actually we need to use the modules, using the property of modules and the definition of intertwining. We can prove that the intertwining operator must be of this form. The worst the singularity is like the variable to non-integral power and also logarithm with polynomial in logarithm. So this is something that one can actually prove, and then see our series is already of a form like the solution of the regular singular points. So here, but I do want to mention one thing. One thing is that actually the module. So you cannot choose. I think that in this case it's fine because the module we assume that. Here is I only assume that the W1, W2, W3, W4 prime to be C1 cofinite. The main thing that there's this intermediate module. Okay, so the main thing that these modules we actually involved, they should something like have only finitely many. There are only finitely many non-integral powers. For rational conformal theory, it is always a direct sum of finitely many irreducible modules. So that's fine. And for the for non-rational case, we have to assume that these modules are actually finite length. But if this is C1 cofinite, one can sort of prove that there are actually the I cannot say that it's a finite length, but see the So I think that I didn't talk about the category of modules we are working with. So to be safe, we always work with finite length module. But the main thing we need is that there are only finitely many non-integral powers, non-integral congruence class for each module. And then see this series will only involve finitely many non-integral congruence class and the polynomial in logarithm. So this is exactly the shape of the regular singular point solution of the regular singular point. And if it's a regular singular point, you compare these, it must be equal, and therefore you can prove that this is convergent. So what another thing is that why this is regular singular point. So I said that this is exactly because you have to prove this using like the here the main thing that here this is E1 to case power. This case power you cannot be arbitrary. So this k sort of like a cancel with this k. So it's here it's a minus k, here it's k. You see this type of property. Make sure that our differential equation is regular singular points.
Do we have any further questions?
Okay.
How about in Zoom? Is there anyone?
Yeah, let me have a look. I don't think there are any questions on Zoom.
Okay, so then let's thank the speaker again.
Okay, thank you. Okay, I'll see you tomorrow.
Thank you very much.
Thanks, Yuji.
Thank you.
Yeah, okay. So here, at least in the in-person events, we have coffee break now, tea and biscuits. We reconvene at 3. Okay, so about 25 minutes from now.